Hello and welcome to the ASML's final video. Modern lithography depends on more power on a smaller footprint. Over here you can see lithography evolves from 3 micrometer all the way to the 5 nanometer today. It's a giant leap forward, but it all depends on the same concept. It is more power on a smaller footprint. Lithography works just like taking a picture old-fashioned way with a giant flashlight. A lithography machine aligns a mask of a certain circuit or a certain pattern and then shoots it onto a silicon chip. Over here is the general layout of a lithography machine. The carbon dioxide laser system will produce laser pulses, and then the laser focusing system will put it into focus, and then the laser will hit a thin droplet, and then the extreme ultraviolet light will be emitted from this thin droplet and then collected by a set of mirrors and then finally sent out. Here's a graphic presentation showing how the laser will hit the droplet. The general requirement of the UV source is that it has to be stable with precise dose control. However, droplet size, shape, and orientation all affect the output of the source. That's why the goal of our project is to analyze the images captured on thin droplets in real time. It can serve as a feedback loop to more precisely control the next generation of the thin droplet. Also, another goal of our project is to formulate target shadow metric between the shape and the source energy. It basically means we need to find what is important and what are the most decisive factors that affect the energy output. One method to analyze the thin droplet images is through ellipse fitting. Ellipse fitting will try to describe the thin droplet through an ellipse. On the images, we can see the ellipse fitting output. It contains the position of the ellipse, the orientation, and the length of the two axes. However, ellipse fitting can be very inaccurate at times. That's why for more complex shapes, we use box fitting. The box fitting will describe the thin droplet in a box. The significance of our project is that we can help to shape more stable targets, which means more stable power output, which will maximize the energy efficiency for the source. Our algorithms are at most 60 times faster than the ASML's original algorithm while maintaining the similar accuracy. Furthermore, we developed a convolutional neural network and the structure shown on the screen. It can predict the energy output upon seeing the images. We can see that the accuracy of our convolutional neural network is very high. We can see that the coefficient of determination of test set is 0.7928. Furthermore, we investigated on the visualization of convolutional neural networks and we generated a heat map for our model. We can see on the heat map that it generalizes all the most popular regions of thin droplet images. It shows the characteristics of 2 most popular categories. That's all for our final product demo video. Thank you for viewing.